Build skills with experts anytime, anywhere. Get certified, get ahead. The world's largest selection of courses, affordable online courses and learning opportunities, top categories.
In our data-driven economy, this combination of skills is in extremely high demand, commanding significant increases in salary as it's revolutionizing the world around us. In this course, you'll learn how to use the principles of data science and the R programming language to answer day-to-day questions about your data. As an overview of this course, first, we'll learn about the practice of data science in the R programming language. Then, we'll learn how to work with data to create descriptive statistics, data visualizations, and statistical models. Finally, we'll learn how to handle big data, make predictions with machine learning, and deploy our applications into production. By the end of this course, you'll have the skills. Whether you realize it or not, there's a flood of data coming our way. In fact, the flood is already here, and it's growing exponentially every year. Over the next few years, we're going to see two entirely different outcomes for individuals, businesses, and governments based on whether they learn to use these data to their advantage or not. Either these people, businesses, and governments are going to sink in the coming sea of data, or they're going to learn how to swim. So I'm currently doing what I can in my professional career to learn how to swim in this new data-driven economy, and I encourage you to do the same. Essentially, in an information economy, data is the new oil. And much like crude oil must be refined into fuel to be of value to us, raw data must also be transformed into knowledge to be of value to us as well. I think Google's chief economist summed the idea up very well when he said, "The ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it. That's going to be a hugely important skill in the next decades, because now we really do have essentially free and ubiquitous data, so the complementary scarce factor is the ability to understand that data and extract value from it." And we see this same sentiment expressed by experts across various industries. In fact, I see articles like these popping up on a daily basis these days. The reality is that there's an extremely high demand for IT professionals with the ability to transform data into actionable insight. However, there are nowhere near enough people available with the proper skills and tools to meet this demand. This means that people with the right set of skills are commanding significantly higher salaries in the IT industry right now. In addition, of all the tools available for transforming data into knowledge, the programming language R is consistently one of the top most used and demanded tools. So I'm glad you've decided to join the data scientists, data analysts, and developers who have learned this valuable set of skills. In addition, I'm very happy to teach you a bit of what I know about data science with R. As an overview of this course, first we'll learn about data science, the data science process, and why it has become so important in recent years. Next, we'll learn about the R programming language, and we'll learn how to program using R. Then, we'll learn how to work with data in order to import, clean, transform, and export data. Next, we'll learn how to analyze our data numerically by creating descriptive statistics. Then, we'll learn how to analyze our data visually by creating data visualizations. Next, we'll learn how to create statistical models to make statistical inferences and predictions using our data. Then, we'll learn how to handle big data scenarios in R, that is, data sets that are too large to process via traditional means. Next, we'll learn how to train machine learning models to make predictions based on our data. Finally, we'll learn how to deploy R into production using a web-based interactive application framework called Shiny. So by the end of this course, you'll have built a web-based interactive machine learning application in R that can take input from a user and make predictions as output. The purpose of this course is to act as a high-level introduction to the most important topics in data science using R. We won't go too deep into any one specific topic. Rather, we'll just learn the most important concepts and defer a much more in-depth coverage of each specific topic to other Pluralsight courses and other sources of information. There are several courses on Pluralsight that provide much more in-depth coverage of each of the main topics we'll cover in this course. So I encourage you to use this course as a high-level guide to get you started with data science using R, and then use the more focused courses for more in-depth training on areas that you are most interested in learning more about. I'll point you in the direction of all the other courses that currently exist on the Pluralsight website and the topics that they expand upon at the end of the last module of this course. The intended audience for this course are developers who want to learn how to use R in the data science process to build data-driven applications, data analysts who want to learn how to use R to perform their data analyses, and IT professionals who want to learn how to make better decisions using data. Essentially, this course is for anyone in information technology with a desire to transform their data into actionable insights using R. Since this is an introductory course, there's no required prerequisites. However, having basic programming experience with at least one programming language will help you understand the programming concepts more easily. In addition, having a basic knowledge of statistics will be beneficial as well. However, if you do not meet either of these two optional prerequisites, you should be able to follow along just fine. So now, let's learn about data science and the data science process. The first question we need to answer is, what is data science? In essence, data science is an interdisciplinary field composed of computer science, math and statistics, and domain knowledge, that is, subject matter expertise, that seeks to derive insight from data. In other words, the goal of data science is to transform data into knowledge that can be used to make rational decisions that lead to beneficial outcomes. The Venn diagram on the screen shows how the three disciplines combine to create the interdisciplinary field of data science. So what then is a data scientist? A data scientist is a person who performs data science for a living. However, a data scientist is more than just a scientist, more than just a data analyst, and more than just a developer. They possess all three sets of skills. Individuals with all three sets of skills and proper credentials are currently very rare in our industry. Despite how rare actual data scientists are, they are currently in very high demand. In addition, that demand is growing every year, as we can see by the trend of job postings on Indeed.com looking for data scientists. So there's clearly a high demand for this specific set of skills, whether you are a data scientist or just applying the principles of data science to your current job role. The rarity of data scientists combined with their high demand leads to much higher salaries that the data scientists and individuals with similar skills can command. It's also important to note that you will not magically become a data scientist after finishing this course. However, this course will teach you basic skills of data science that you can begin applying at your job today, and will point you in the right direction if a career in data science is something you're interested in learning more about. So what set of skills does a data scientist possess? In general, the skills of data science are programming computers using a programming language like R, working with data, that is, collecting, cleaning, and transforming data, creating and interpreting descriptive statistics, that is, numerically analyzing data, creating and interpreting data visualizations, that is, visually analyzing data, creating statistical models and using them for statistical inference, hypothesis testing, and prediction, handling big data, that is, data sets that are too large to work with via conventional means, making predictions using machine learning algorithms, and deploying their work into production environments or communicating their results to a wider audience. If you recall from the outline of this course we saw earlier, we're going to be touching upon each of these skills throughout the remaining modules of this course. Regarding the tools used in data science, here are the tools listed by the respondents of O'Reilly's Data Science Salary Survey in 2015. On the x-axis, we have the name of the tool, which includes programming languages, data platforms, or analytics tools. On the y-axis, we have the percent of respondents reporting that they use that corresponding tool. As we can see, R is listed as one of the most popular tools used for data science. In addition, across a variety of similar surveys I've looked at, we see the same four tools at the top of most surveys. Typically, we see SQL first, followed by Excel, and then both R and Python are usually pretty neck and neck in terms of their popularity. So why has data science become so important all of a sudden? There are a few trends really driving the importance of data science. First, emerging trends like the Internet of Things are creating massive amounts of relatively low-cost data. This means that we now have access to large amounts of valuable, low-cost, near real-time data. Second, emerging trends like big data are creating new tools like Hadoop that allow us to process big data sets at scale. This means that we can process these massive data sets with relatively low cost and in a reasonable amount of time. Third, we have powerful machine learning tools that can find patterns and make predictions with these data. Emerging trends like deep learning via deep neural networks are making machines significantly better at making predictions than humans in certain categories of decision making. Finally, in the past, we would collect data and analyze it so that human beings could use the results of the analysis to make a decision and take action. However, we're now closing the loop of the Internet of Things, big data, and machine learning so that human beings are no longer required in the decision-making process. This leads us to fully autonomous systems and environments that function without the need for a human decision maker in the process. These fully autonomous systems will transform our world in more ways than I could possibly enumerate. Self-driving cars, intelligent buildings, and smart cities are either already here or just around the corner. In fact, it's a very exciting time to be learning about data science. Essentially, the recent importance of data science all boils down to two things. It's being driven by economics, and it's being made possible by technology. The cost of collecting, storing, processing, and analyzing data is continuously decreasing. And the value that these data can provide, when the data science process is applied correctly, continues to increase. In addition, we now have the technological capabilities to close the loop to create fully autonomous systems. The cost savings and value-generating possibilities of these fully autonomous systems are very compelling. Given this, it's unlikely that the demand for data science will decrease anytime in the near future. The data science process works like this. First, we find a question that we want to answer. This can be a hypothesis we want to test, a decision we want to decide on, or a prediction we want to make. Second, we explore the data that we have available and the data that we may need to collect. We need to understand what data we have, what data we don't have, and what condition these data are in. Third, we prepare the data for analysis, a process often referred to as data munging or data wrangling. We need to gather, clean, and transform these data to get them into a form suitable for analysis. Fourth, we create a model given our data. In the most generic sense, this can be a numerical model, a visual model, a statistical model, or a machine learning model. Fifth, we evaluate the model. We need to determine if our model answers our question, helps us make an informed decision, or creates an accurate prediction. In addition, we also need to make sure that the model is appropriate given our data and the context. Finally, if everything looks good, we deploy our model. This could mean either communicating the results of our analysis to others, making a decision, or implementing an application in production. Then, we repeat this process for each question we'd like to answer. This is typically an iterative process. We typically go through the complete cycle multiple times, learning and improving with each iteration. In addition, this process is often non-sequential. We often have to bounce back and forth between steps as we discover problems and learn better ways of solving these problems. Sometimes we don't always need to complete the process. Often, we learn that what we're doing isn't working or doesn't make sense given the data or the context. So we terminate the process and shift our focus to the next most important data science question. There are also some well-established practices for the data science process available, like the CRISP-DM process, which stands for Cross-Industry Standard Process for Data Mining. These established practices are useful to help you get started with your data science process. In this module, first, we introduce the topic of this course and explain why we want to learn about data science and R. We discuss the factors that are driving the demand for both data science and tools like R. Next, we provided an overview of the course. We discussed the course outline, intended audience, prerequisites, and more. Finally, we introduced the topic of data science. We learned what data science is, why it has become so important, and how the data science process works. In the next module, we'll learn about the R programming language and how to use it for data science. The first question we need to address is, what is R? R is a free, open-source implementation of the statistical programming language S. S was a statistical programming language invented in Bell Labs in 1976, so R is the free, open-source implementation of that language. R is both a programming language and an environment within which to program. That is, we have a programming language called R and a development environment for that language, which are both referred to as R. It provides both numerical and graphical data analysis capabilities. That is, we can analyze our data statistically, or we can analyze data visually by creating data visualizations. It's also cross-platform, which means it runs on Windows, Mac, and Unix systems. In addition, R is actively under development, has a large user community, is very modular and extensible, and has over 9,000 extension packages. And best of all, R is free open source software, meaning that it's free, as in beer, meaning anyone can use the software without cost, and free, as in speech, meaning anyone can view the source code, learn from it, modify it, or redistribute it as they wish. As I mentioned earlier, R is a very popular programming language, so in order to show where it lies in terms of programming language popularity, here's a data visualization from RedMonk showing us where R lies relative to other programming languages. On the x-axis, we have programming language popularity on GitHub by number of projects. On the y-axis, we have the popularity rank on Stack Overflow by number of tags. As we can see at the upper right-hand corner, we have the very popular general-purpose programming languages, for example C#, Java, and Python. In this next cluster, we have the popular, more specialized languages, for example MATLAB, Lisp, and Erlang. And finally, down here, we have the less popular languages. Here we have R, right at the top of the more popular specialized languages. In addition, I should also note that R will most likely never be as popular as the general-purpose languages. It's specialized to work with data extremely well, but you probably won't be using it to build your next e-commerce website anytime soon. This is what R looks like. As you can see, we have both a programming language and an environment within which to program. In addition, we can see that R can do both numerical analysis and graphical analysis as well. Rather than working with the out-of-the-box R IDE for the demos in this course, we're going to be using a more powerful integrated development environment, or IDE, called RStudio. It still uses the R programming language, however, the IDE is much more user-friendly and makes it much easier to do code demos. We'll walk through the various windows in RStudio during the first code demo, which is coming up shortly. In addition, I think it's important that I should point out that there's now support for R in Microsoft Visual Studio using R Tools for Visual Studio, or RTVS for short. If you're a software developer that uses Visual Studio as your primary IDE, you might prefer to use R in Visual Studio instead. There are pros and cons to each of these three IDEs, however, I'll leave it up to you to try each of them out and choose which one you're most comfortable with. Before we begin our demos, we need to download and install both R and RStudio. You can download R from the R project website at www.r-project.org. Downloading and installing R on your computer is relatively easy and straightforward, so we won't cover these steps in our upcoming demo. Ultimately, I don't think you should have any difficulties getting R up and running if you follow along with the instructions included. Next, we need to download and install RStudio. You can download RStudio from the RStudio website at www.rstudio.com. Once again, the installation is easy and pretty straightforward. So we'll pause here to give you a chance to get your computer set up in the event you'd like to follow along, and then we'll see a demo of the R language basics next. For our first demo, we're going to complete a Hello World example using the R programming language inside of the native R development environment. After this demo, we'll be using RStudio going forward for the remaining demos in this course. To perform Hello World, we want to set a variable x equal to the character string Hello World and then print this variable to the console window. First, we type into the console x followed by the left arrow assignment operator, then Hello World surrounded in double quotes. When we press enter, the character string Hello World is stored in a variable named x. Next, we type the print function and pass x in as an argument to the function. When we press enter, the value that was assigned to the variable x, that is Hello World, will be output to the console window. Successfully printed Hello World to the console using a variable in R. So now let's switch from the native R development environment to RStudio to make things easier for the remainder of our demos. This is the RStudio Integrated Development Environment, or IDE for short. There are four main window panes in RStudio. First, in the upper left-hand corner, we have the source pane. It contains the scripts that will be running for each of our demos. Next, in the lower left-hand corner, we have the console pane. This is where we can interactively program in R. We type commands and output appears in the console window. Then, in the upper right-hand corner, we have the environment pane. The environment pane shows us the state of all the variables that are currently in memory. Finally, in the lower left-hand corner, we have the miscellaneous pane. Here, we find tabs for navigating the file system, viewing charts and graphs, and reading the help documentation. In order to make the code demos run more smoothly, we're going to be executing scripts from the scripts pane line by line rather than typing everything by hand. We could do everything by hand like in the Hello World demo, but typing during demos is error-prone and doesn't help move the demos along any faster. It'll work like this. I'll place my cursor on the line of script I plan to execute, and I'll press Ctrl plus Enter, which will execute that line of code in the console. You'll see both the command being executed and the results of the command in the console window. To see how this will work, let's just walk through the Hello World demo again in RStudio. First, in the console, we'll set x to the character string Hello World. Next, in the environment pane, we'll see that the variable x has been assigned to the value Hello World. Then, in the console, we'll print x, which writes Hello World to the console window. Easy enough? Excellent! Now let's take a look at the basic language features in R. As we saw in the Hello World demo, we can assign a value to a variable using the left arrow assignment operator. This operator assigns the value on the right to the variable on the left. In addition to the left arrow assignment operator, there are two other value assignment operators in R. The second assignment operator is the equal sign assignment operator. For the most part, the equal sign assignment operator behaves similar to the left arrow assignment operator. However, there's a slight technical difference regarding the scope of the variable's assignment. This technical difference is a bit difficult to explain, especially if you don't have a background in programming, so we'll defer an explanation for now. As a general rule for this course, however, always use the left arrow assignment operator unless you see me using the equal sign assignment operator, which we'll do from time to time, for example, when creating columns for a data frame. There is also a third assignment operator called the right arrow assignment operator. This operator assigns the value on the left to the variable on the right. However, this operator is rarely, if ever, used, so I recommend avoiding it in general. For all of our demos in this course, we'll be using the left arrow assignment operator exclusively, except in cases where we specifically need to use the equal sign assignment operator. R has a language feature called implicit printing. Rather than having to type print x every time we want to write the value of a variable x to the console, which we refer to as explicit printing, we can implicitly print the variable instead. Implicit printing allows us to simply type the name of the variable, for example x, and when we press enter, the value of the variable is automatically printed to the console. We'll be using implicit printing for the remainder of this demo. However, we'll use explicit printing in later demos to make it more clear what is occurring during those demos. To create variables in R, we just assign a value to a variable. For example, we can create a logical, that is, a Boolean variable, and set its value to either true or false. We can create an integer variable by setting its value to an integer and using the capital letter L suffix. The L stands for long, which is programming language shorthand for long integer, which is a 32-bit integer. Integers are either positive or negative whole number values. We can create a numeric variable by setting its value to a numeric constant. Numeric variables contain decimal precision numeric values. We can create a character string by setting its value to a string of characters surrounded by double quotes. The character data type can store an arbitrary length string of characters. And we can create date and time data types in R as well. For example, to create a date representing February 3rd, 2001, we use the asDate operator and pass in a date in one of the many date-time formats recognized by R. There are a few other primitive data types as well. For example, data types for working with both dates and times together and for dealing with complex numbers. But these 5 data types are the most frequently used ones in the language. In addition, these are the only data types that we'll be using for the demos in this course. Once we have created variables, we can display the value of these variables in the console by either explicitly or implicitly printing them. For example, our logical variable prints the value true, as we'd expect, our integer variable prints a whole number, our numeric variable prints a decimal precision numeric value, our character vector prints out a string of characters, and our date data type prints out a date in the ISO 8601 International Standard Date format, that is year, month, and day separated by dashes. R is a functional programming language, so functions are first-class citizens in R. This means that we can assign functions to a variable and pass them around just like variables containing data. We create a function by using the function keyword and defining the arguments and the body of the function. For example, to create a function f with a single argument x and a body that returns x plus 1, we type f set equal to a function with the argument x and a body that returns x plus the number 1. Now, if we want to invoke that function, we simply type the name of the function f and pass in an argument for x. In this case, we passed in the value 2, so 2 plus 1 returns 3. In R, we can assign functions to named variables, or we can use anonymous functions as well. That is, we can use a function without first assigning it to a named variable. In addition to primitive data types and functions, we have more complex data structures in R as well. Data structures are containers that hold a collection of data in one of several ways. The most important of these data structures in R is a vector, which is essentially a one-dimensional array containing elements of the same data type. To create a vector, we use the concatenation function C and pass in a comma-separated list of homogeneous values, that is, values that are all of the same data type. This function combines each of the individual elements into a vector containing those elements. For example, to create a numeric vector containing the values 1, 2, and 3, we set v equal to a vector containing the values 1, 2, and 3. When we print the variable v, we see a vector containing the values 1, 2, and 3. We can also create a vector of numerically ascending or descending values using the sequence operator, which is the colon character. For example, to create a vector containing the values 1 through 5, we set a variable s equal to the values 1 through 5. When we print this variable s, we see a vector containing the numeric values 1 through 5 in ascending order. Next, we can create a matrix, which is a special case of a two-dimensional array using the matrix keyword. For example, if we want to create a 2x3 matrix containing the values 1 through 6 populated in columnar fashion, we'd set a variable m equal to a matrix containing the sequence of data 1 through 6 with 2 rows and 3 columns. When we print this variable m, we see a 2x3 matrix containing the values 1 through 6 populated in columnar fashion. We can create multidimensional arrays in R using the array keyword. Arrays can have 1, 2, or more dimensions. For example, if we want to create a 2x2x2 array, that is, a 3-dimensional array containing the values 1 through 8 populated in columnar fashion, we would set a variable a equal to an array with the data 1 through 8 and set the dimensions argument equal to a vector containing the values 2, 2, and 2. When we print the variable a, we see a 2x2x2 array containing the values 1 through 8 populated in columnar fashion. In addition to creating data structures with homogeneous data types, that is, data structures that contain values of all of the same data types like vectors, matrices, and arrays, R also contains a special data structure called a list for storing collections of heterogeneous data types, that is, a list of values of different data types. For example, to create a list of heterogeneous values in R, we would set a variable L equal to a list containing the logical value true, the integer 1, 2, 3, the numeric value 2.34, and the character string ABC. When we print the variable L, we see a list containing the values true, the integer 1, 2, 3, the numeric value 2.34, and the character string ABC. The formatting of the output of a list in the R console might look a bit messy and difficult to read. However, this formatting has to do with the way R stores the values contained in the list within memory. There's a special data type in R called a factor that stores categories of named values. This is similar to an enumeration in the C-like programming languages. Factors store a list of categorical variables by assigning each unique category, called a level, as an integer value and storing the data as a vector of integers in memory, instead of storing the entire list of categorical values. Doing so saves a significant amount of space in memory and affords significantly greater performance for many operations. For example, if we have a vector of character strings containing the named values male, female, male, male, female, we can store these values using a factor. First, we set a variable called factors equal to the factor keyword given a vector of character strings. If we print this factor, we can see that it contains 5 values male, female, male, male, female, and 2 levels, that is, female and male. If we use the levels command, we'll see a list of unique named values or levels in alphabetical order. The order in which these named values occur is the order that maps to the backing integers. For example, female maps to the integer 1 and male maps to the integer 2. If we use the unclass command, we can see the underlying integer array, that is 2, 1, 2, 2, 1, and the 2 levels, that is female and male, that compose this factor. We'll be using factors to store all of the categorical values that we'll be working with in this course. A data frame is the most important data structure for working with collections of tabular data in R. It essentially represents a table of data, that is, it has a set of columns and a set of rows. Each column can contain a different data type, but all of the data in a single column must be of the same data type. We create a data frame using the data frame keyword. For example, we can set a variable df equal to a new data frame containing a column called name, populated with a vector of character string values cat, dog, cow, and pig, and a second column called how many, containing a vector of integers 5, 10, 15, and 20, and a third column called isPet, containing a vector of logical values true, true, false, and false. When we print our data frame, we get pretty much what we'd expect, a table containing 3 columns, that is, name, how many, and isPet, and 4 rows containing their respective values. Once we have our data stored in a data frame, we can query and manipulate these data in extremely powerful ways. We can index our data frame by row and column using the index operator. For example, if we want to return the value contained in row 1 and column 2, we would type the following. As we can see, this returns the integer 5, which is the value contained in row 1 and column 2 of our data frame. In addition, we can omit the column argument, and the index operation will return the values in the first row across all columns. Or we can omit the row argument, and the indexing operation returns all values contained in the second column. We can also index by columns using the column name with the double square brackets notation. Or there's a syntactic shortcut that allows us to use the $sign followed by the name of the column. All 3 of these examples return the same values, that is, all rows in the second column. However, the last of these 3 methods is generally preferred. One of the most powerful language features for querying data in a data frame is called subsetting. Subsetting allows us to slice and dice data in very flexible ways. First, we can pass a vector of integers indicating each row we want returned from our data frame into the rows argument of the index operator, and it will return the specified rows. For example, passing in a vector containing the integers 2 and 4 will return rows 2 and 4. In addition, we can pass a sequence of integers, for example rows 2 through 4, into the rows argument, and it will return rows 2 through 4. We can also pass in a vector of logical values, for example true, false, and false, indicating which rows we want returned or not. And it will return the corresponding rows. In this case, row 1 and row 3, since the first and third elements in the vector were set to true. Although passing a vector of logical values by hand might seem like a trivial example, you can imagine how powerful this would be if the values in the vector were created programmatically, using an operation that returns true or false for each row in the database. For example, we can use the equality operator to return true or false for each row in the database matching a certain condition. As an example, we could specify that we want to return all rows where isPet is true, and we'll get the rows containing cat and dog. We can also subset using inequality operators. For example, we can query all rows where how many is greater than 10, which returns the rows containing cow and pig. We can also subset data tables using more advanced query expressions like finding all rows matching a list of values. For example, we can find all rows where the animal's name is contained in the list cat or cow, and this will return just row 1 and row 3. And I should note that indexing and subsetting operations also apply to vectors, matrices, arrays, and lists in addition to data frames. A very important thing to note about R is that it's a vectorized language. This means that all atomic data types in the language are vectors of size 1. What this means is that every time we assign a single value to a variable, we aren't actually assigning a single atomic data type to the variable like we would in most other programming languages. Instead, we're creating a vector of the specified data type and assigning the value to the first element of the vector. Now, this might seem a bit odd at first because this is very different from most programming languages you've probably worked with. However, it makes perfect sense in R because we're typically working with collections of data. For example, vectors, matrices, arrays, lists, and data frames, so working with them as collections is often more practical and efficient. For example, if we add the values 1 and 2, we get the value 3 like you would expect. However, this 3 is actually a vector containing a single element with a value of 3. In addition, most operations in R are vectorized, meaning that they take a vector as input and return a vector as a result. For example, if we were to add a vector containing the values 1, 2, and 3 to a vector containing the values 2, 4, and 6, we'd get a resulting vector containing the values 3, 6, and 9. This is because the pairwise addition of 1 and 2 is 3, 2 and 4 is 6, and 3 and 6 is 9. Another important language feature to note is named versus ordered parameters. With R, we can either pass arguments into functions using the name of the parameter, or we can pass arguments into functions by their default order. We learn the default order of parameters by looking at the help files for each command. For example, earlier we created a matrix with the data 1 through 6 with the number of rows equal to 2 and the number of columns equal to 3. However, we can also create an identical matrix passing the same values by their default order, provided that we know the correct parameter order, which is available from the help files. Now, if we check to see if the elements of these two matrices are equal, which they should be, we can see that we get a matrix back with the value true in all cells. This is because the pairwise equality of each value in each cell in both of these matrices is true. Notice that the equality operator for matrices is vectorized as well. We gave it two matrices and it returned a matrix as the result, instead of either a single true or false answer. However, if you're interested in testing if these two matrices are indeed identical, that is the scalar equivalent to the vectorized equality operation, we can see that the operation returns true as the two matrices are indeed identical. The fact that R is a vectorized language is one of the most interesting and powerful features of R. However, it is one of the most confusing aspects for both developers and non-developers new to R, as it takes a bit of time to get used to. In fact, because of this feature, it is very rare that you use for loops in the language. This is quite different than most programming languages you've probably used, where iterating over collections is a very normal part of programming. If you really want to understand the power of R for processing data, it's important to have a solid grasp on this concept. As I mentioned earlier in this module, R is very modular and extensible. It's very easy to download and install packages that contain new functionality that extends the power of the language. For example, if we would like to install an extension package called dplyr, which we'll be using for our next demo, we would just type install.packages and specify the name dplyr. When we press enter, R will go online to the CRAN repository, which stores all of the public R packages, and download and install dplyr on our machine. Once a package has been installed, to use it in our code, we simply type library and specify the package we want to load in memory. Now we have access to all of the commands and features found in the dplyr package. If you need help with any of the commands in R, just type question mark and the name of the command that you need help with. This will pop up the online documentation for that command in the help pane in the lower right-hand corner. From there, you can learn all about the commands, their arguments, return values, and more. Other than what we've seen in this demo so far, R contains most language features you'd expect from other C-like programming languages. For example, control structures like if-then-else statements, for loops, while loops, and switches, mathematical, relational, and logical operators, and string manipulation functions with regular expressions. The R language has evolved quite a bit over the years, and there are many more language features available than we have time for in this brief overview. When we're working with data prior to performing a data analysis, there are typically 4 main steps we perform in R. These 4 steps are often necessary to transform our raw data into a form suitable for analysis. First, we need to import our raw data from one or more data sources into R. Next, we need to inspect and then clean our raw data so that we can work with it effectively and produce reliable results. Then, we need to transform our clean data into a form suitable for the analysis we intend to perform. Finally, we often need to export our data into a different format so that it can be shared with others. You'll often hear these steps referred to as data munging, data wrangling, data cleaning, data cleansing, or ETL, that is, extract, transform, and load, depending upon the context and the specific user community. All 4 steps may not always be necessary, but in general, we'll typically use some combination of these 4 steps. Next, we'll take a look at each of these 4 steps and how R makes our job easier during each of these steps. The first step when working with data in R is to import our data into R. Luckily for us, R makes it very easy to import data from a wide variety of data sources. We can load data from file-based data sources such as comma-separated values, tab-delimited values, and Excel files, web-based data sources, for example XML, HTML, and JSON data, databases, for example SQL Server, Oracle, and MySQL, and statistical data files like SAS, SPSS, and Stata files. And there's many more. In fact, there are literally hundreds of data sources that R supports using downloadable extension packages. In addition, R is very flexible in the way that it can load data, which allows it to handle a wide variety of data scenarios. The second step when we work with data in R is to clean our raw data so that we can work with them effectively and ensure that they will provide reliable results. This step is often necessary because most raw data are not typically stored in a format suitable for analysis. In addition, many raw data sources contain errors and anomalies that need to be corrected in order for our analysis to produce reliable results. There are many tasks typically involved in the process of cleaning data. Some of these tasks include reshaping data so that we have a table of data with each variable stored as a column and one observation per row, renaming columns so that we have accurate and human-readable column names, converting data types from one data type to another, that is, converting between logical values, integers, numerics, character strings, dates, times, and factors, ensuring that all data types are properly encoded, for example, converting the letters M and F to the categories male and female, respectively, ensuring all data are internally consistent by converting to the same unit of measure, the same numeric scale, and using the same internal format for numbers, dates, and times, handling both errors in our data and correcting outliers, for example, values that were incorrectly typed into a computer by hand or were the result of a sensor misreading, and handling missing values either by omitting the entire row or imputing a suitable replacement value. R has a series of built-in tools and extension packages that make cleaning our data significantly easier than by using alternative methods or by cleaning the data by hand. We have a wide variety of built-in functions in the base packages in R, that is, the packages that are part of the initial R installation. These functions include functionality for handling many of the data cleaning tasks that we just discussed and more. In addition, we have several extension packages, that is, packages that are not part of the base installation that must be downloaded and installed, designed to help with more specific data cleaning tasks. For example, we have extension packages like tidyr, which is focused specifically on tidying data, that is, reshaping data from a variety of non-standard formats to a standard tabular data format referred to as tidy data. That is, we have all variables on the columns in one row for each observation. Reshape2, which offers the same functionality as tidyr, but provides more functionality for reshaping and aggregating data at the expense of a more complex syntax than tidyr. Stringer, which provides a simple and consistent set of commands for character string manipulation, Lubridate, which provides a simple and consistent set of commands to work with dates, and Validate, which allows you to create a set of reusable domain rules to check if your data adhere to those expected rules. The third step when we're working with data is typically to transform the data into a form suitable for analysis. This typically involves several steps, including selecting the columns that we want to include in our analysis, filtering the rows that we want to include in our analysis, grouping data together based on one or more columns and aggregating the results within each group, ordering the rows of our data by one or more columns, which we refer to as sorting or arranging, and merging one or more tables of data together. There are several other tasks that we might perform during the data transformation process. However, these are the most common tasks. In addition, there's a lot of overlap between the data cleaning and data transformation steps. In fact, many people simply group these into a single task. What's most important is that you end up with data that is both clean and transformed into a format suitable for analysis. There are several built-in functions and extension packages available in R to help us transform our data. For example, the base R installation contains functions for selecting columns, filtering rows, grouping rows, and sorting rows as well. We saw a few of these functions during our previous demo on subsetting data frames. Plier provides tools for splitting, applying, and combining data within R. dplyr is the next iteration of Plier designed to provide a consistent grammar for data manipulation using data frames, data tables, and databases. It has several improvements over its predecessor Plier. Data table provides similar functionality to both Plier and dplyr, but has a syntax similar to the subsetting syntax we saw in our previous demo on subsetting data frames. And the SQLDF package allows us to execute queries using SQL, that is structured query language, on data contained within our data frames. It's useful to know all 5 of these methods for transforming data in R. However, we'll be focusing specifically on dplyr during our upcoming demo since it's both very powerful and yet easy to understand. The fourth and final step when working with our data is often to export our cleaned and transformed data into a new data repository. We don't always have to perform this step, for example if we move right into analyzing the data after we've imported, cleaned, and transformed the data. However, many times we want to share our cleaned and transformed data so that others can analyze these data. Once again, luckily for us, R makes exporting data extremely easy by providing us with support for a wide variety of data repositories. We again have support for file-based data formats like CSV, tab, and Excel files, web-based formats like HTML, XML, and JSON, databases, for example SQL Server, Oracle, and MySQL, statistical data files, for example SAS, SPSS, and Stata files, and many more. Before we transition into our demo, let's take a quick look at dplyr and what it can do to help us with our data transformation process. dplyr is a popular extension package for R that is designed to provide a consistent grammar for data manipulation. It was designed to work with data frames, data tables, and with supported databases. It's very similar to SQL, that is structured query language, in terms of both its function and purpose. dplyr is composed of a set of verbs that allow us to manipulate data within a single table or across multiple tables. The single table verbs in dplyr include, but are not limited to, select, which selects a subset of columns from our table, that is, it creates a projection, filter, which selects a subset of rows from our table, that is, it filters the data based on a set of criteria, mutate, which creates a new column by transforming data in existing columns into a new form, summarize, which allows us to summarize or aggregate a set of rows that are grouped together using a common value, and arrange, which reorders the rows in a table based on one or more columns and an order within which to sort them. The multi-table verbs, which operate on 2 or more tables, include operations you'd expect like joins, union, intersection, and set difference. However, we're just going to focus on the single table verbs during our upcoming demo. Unfortunately, preparing your data for analysis is often the most difficult and most time-consuming step in the data science process. In fact, most data scientists, data analysts, and consultants, myself included, report spending about 80% of our time on average on this step alone. The unfortunate reality is that while data science seems like a glamorous job, most data scientists spend most of their time doing data janitor work just to get their data prepared for analysis. So my recommendation to everyone is to record all steps using a script so that you can reapply the steps whenever they are needed. Because it is inevitable that you'll be on step 50 of a complex data analysis and realize that you've made a mistake back in step 5. You don't want to have to go back and reapply every step by hand. You just want to make the change at step 5 and rerun the script instead. In addition, once you've performed a data analysis, you'll likely be asked to perform it again a year later with the latest data. If you have your data transformation steps recorded as a script, you can just point it at the new data and rerun the script. So now, let's see how to transform our new data in R using dplyr. For the next few demos in this course, we'll be using a very popular dataset in R called the Motor Trend Cars dataset. This dataset was collected from cars contained in Motor Trend magazine in 1974. These data contain a series of measures from 32 cars released between 1973 and 1974. However, for our demo, we're just going to be using a subset of these measures to keep things simple. Our dataset will contain 4 columns, which are referred to as variables in this context. Name, which is the make and model of the car. Transmission type, which is a categorical variable containing manual for a manual transmission and automatic for an automatic transmission. Cylinders, which is an integer representing the number of cylinders contained in the car's engine. For example, a V6 engine would be represented as the integer 6. And fuel economy, which is a numeric data type which represents the rate at which the car consumes fuel measured in US miles per gallon of fuel. The dataset contains 32 rows, 1 row for each car contained in the dataset. During this demo, first we're going to import our data from a tab-delimited flat file. Next, we'll transform our data using dplyr. Finally, we'll export our data to a comma-separated values file that is a CSV file. Cleaning data can often be a long and complex process, so I've chosen to omit this step for our demo to keep things moving along and interesting. I just want to show you the most important aspects of using R right now, so that you can choose to invest time learning how to clean data from a more in-depth course later if you choose to do so. I'll point you towards these more in-depth courses for cleaning and transforming data in the last module of this course. First, let's take a look at the tab-delimited flat file that we're going to be using as our data source. As we can see, we have a text file document containing a header. That is, the names of the columns are contained in the first line of text in the file. We have 4 columns of data in our data set. That is name, transmission, cylinders, and fuel economy. Each column is separated, that is delimited, by the tab character, which is represented in the text editor as an orange arrow. The end of each row of data is delimited by the carriage return line feed character sequence, which is represented by the CR and LF symbols. The file contains 32 lines of text for each of the 32 rows of data, plus 1 extra line for the header. In addition, text data is denoted by using the double quote character on both sides of the textual data. This type of file is pretty standard for exchanging data in the IT industry. So now let's switch over to R to begin working with these data. To begin working with file-based data, first we need to set our working directory to the directory on our computer that contains our data files. We're going to be using a directory called Pluralsight located at the root of the C drive of our computer for all of the demos in this course. We set the working directory using the setwd function, and we pass in the path to our directory into the function as an argument. For example, in our case, we'll pass in c:/Pluralsight as our working directory. Please note that in R, we typically use the / character as our path separator character even when we're using a Windows-based system. This is because the / character is used to indicate a character escape sequence, so using the / is simpler and easier to read. Next, we need to import the data into R. As we mentioned earlier, there are a wide variety of ways to load data into R. We're going to be loading a tab-delimited data file, so we'll use the read.table function, set the file name parameter to cars.txt, which is the name of the tab-delimited data file, set our header parameter to true, indicating that our first row contains the column names for our data set, set the separator parameter to the tab character, which is represented by the character escape sequence \t. This tells R that the columns of data are separated by the tab character. And set the quote character, that is, the text delimiter, to the double quote character using the character escape sequence \double quote. This tells R that anything contained inside of a pair of double quote characters should be interpreted as text, including special characters like the tab character. We'll then assign the data that we've loaded into a data frame called cars. Now, let's take a quick peek at these data that we've loaded. We'll do this using the head function, which displays just the first 6 rows of data. As we can see, we have 4 columns, that is name, transmission, cylinders, and fuel economy. In addition, we can see the first 6 rows of our data. To begin transforming our data, we need to load the dplyr package. We already downloaded and installed this package during our previous demo, so we don't need to do that again. In addition, going forward in these demos, I'm going to skip the download and install steps and move right into loading packages into memory. This will help keep things moving along more quickly. We do, however, still need to load the dplyr package into memory. We'll do this using the library function and pass in dplyr as an argument. Now we have access to all of the functions and features of the dplyr package. We're going to transform our data step by step, performing one transformation step and then inspecting the results of each step to see the results of our transformation. To transform our data, we're going to select just 3 columns that we want to work with, that is, transmission, cylinders, and fuel economy. We'll do this using the select function in dplyr. Set our data parameter to our cars data frame, and please note that with dplyr, our data parameter is actually .data rather than just data, which was done intentionally to avoid name collision. Then we'll specify the 3 columns that we want to keep from the 4 columns available in our data frame. We separate each column name using a comma, and we'll assign the results of this transformation to a variable called temp for temporary. Now, let's see what the results of this transformation look like using the head function on our temporary variable. As we can see, our results contain only the 3 columns we specified, that is, transmission, cylinders, and fuel economy. Next, we'll filter our data to include only cars with automatic transmissions. We'll do this using the filter function, set our data parameter to our new temporary data frame, and we'll add a filter predicate specifying to include only records where transmission is equal to automatic. And please note that we could have used one of many types of predicate functions, including inequality operators and more complex matching expressions. Now let's take a look at the results of our filter transformation. As we can see, we now have only rows where transmission type is set to automatic. Next, we'll convert our fuel economy values from US miles per gallon of fuel to the metric equivalent fuel consumption in kilometers per liter. We'll do this using the mutate function, set our data parameter to our temporary data frame variable, set our mutation expression to consumption set equal to fuel economy times 0.425. This tells dplyr that consumption will be the name of the new column we are creating, using the existing fuel economy column and multiplying each value by 0.425, which is the conversion factor from miles per gallon to kilometers per liter. In addition, please note that the phrase fuel consumption is the metric equivalent name for what is referred to as fuel economy in the US, hence the new column name. Now, let's inspect the results of this transformation. As we can see, we now have a fourth column called consumption that contains the metric equivalent of each fuel economy value. Next, we'll group our rows of data by the number of engine cylinders that each car contains. We'll do this using the group by function, set the data to our temp variable, and set group by to our cylinders variable. Now let's inspect the results. As we can see, our results have changed from our familiar format to something that looks slightly different. This is because the group by function returns a grouped data frame rather than a regular data frame as its result. The printed output of our group data frame tells us that the data source is a data frame with 6 rows of data being displayed, which is the default for the head function, and 4 columns of data. It also tells us that the number of groups in the result is 3, that is, we have 4, 6, and 8-cylinder engines. In addition, it also tells us the data type of each column under the column name, that is, factor for transmission, integer for cylinders, double, which is an alternative name for a numeric variable for fuel economy, and double for consumption. Now that we have our data grouped, we can summarize the values contained in each group. We do this using the summarize function, set our data parameter to our temp variable, and set our summarization expression to average consumption set equal to the arithmetic mean of consumption. This tells dplyr to create a column in our results called average consumption, which will contain the average consumption for each group of cars by the number of engine cylinders they contain. Now let's take a look at the results of our transformation. As we can see, we have a new data structure called a tibble, which contains 3 rows and 2 columns. A tibble is a modern take on a data frame that contains all of the best features of a data frame, but eliminates some unnecessary features. This tibble contains 2 columns, that is cylinders, which is an integer, and average consumption, which is a double, that is a numeric value. The 3 rows, of which there is 1 for each number of cylinders, contain the average fuel consumption in liters per kilometer for all cars in each group based on the number of cylinders they possess. Next, we'll arrange the order of the rows so that we sort our rows by average fuel consumption in descending order. That is, we want the most fuel-efficient vehicles on the top and the least efficient on the bottom. We'll do this using the arrange function. Set our data parameter to our temporary variable, and set our sort expression to average consumption in descending order. Now let's take a look at the results of this transformation. As we can see, we have our tibble of data sorted by average consumption in descending order. However, since our data was already in this order merely by coincidence, we didn't really see any changes from our previous results. Finally, we'll convert our tibble back into a data frame. We'll do this using the asDataFrame function, passing in our temporary variable as an argument. Then, we'll assign the result to a new variable called efficiency. Now, let's inspect the results of this final transformation. As we can see, we've converted our transformed data contained in a tibble back into a data frame. So far in this demo, I've shown you how to use dplyr in a step-by-step manner, calling out each step and each parameter involved in each step. While this made the initial demonstration more clear and straightforward, it is, however, both inefficient and not as easy to read when creating production code. dplyr is a grammar for data manipulation, and as such, we can write our data manipulation code in a much more succinct way by using what is referred to as fluent notation using piping, also known as method chaining. The pipe operator in dplyr is the % right angle brace % character sequence. We can pipe each of our dplyr functions together line by line to create a much more readable chain of commands. To demonstrate how this works, we'll execute the exact same set of commands that we used previously. However, this time we'll chain the commands together using the pipe operator instead. We'll start by assigning the results of our data manipulation to a variable called efficiency, set our data source to our cars data frame, select the 3 columns, filter to include only automatic transmissions, mutate to create our metric fuel consumption variable, group by cylinders, summarize by the average consumption of each of our cylinder groups, arrange our rows by average consumption in descending order, and convert our results to a data frame. Now let's inspect the results of this changed set of commands. As we can see, the chain version of our command produces the exact same results as our step-by-step commands. Finally, we'll export the results of our data transformation steps to a comma-separated values file. We'll do this using the write.csv function, set our x parameter to our efficiency data frame. Please note that the parameter x is just a generic parameter name for the data we want to save, set our file name to fuelefficiency.csv, and set our row name parameter to false, indicating that we do not want to write the unique ID for each row to our CSV file. Now let's open up this CSV file to see the results. As we can see, we now have a comma-separated values file containing the results of our data transformation. The file contains a header row specifying the names of our two columns, that is, cylinders and average consumption. Each field of data is separated using a comma, and each of our rows is delimited using the carriage return line feed character sequence. This is just a small taste of the power that R provides to import, clean, transform, and export data. There's so much more that I'd like to show you. However, in order to keep things moving along, we'll have to defer this additional information to a more in-depth course on working with data in R. I'll point you in the direction of these courses during the end of the last module of this course.